Yes, we use the longitudinal twin study and sensorimotor synchronization as musical performance. Before we start, I would like to give you a short summary of the structural brain measures. I don't know who's familiar in this group with all the brain measures that we use, but in our lab, and mainly I do, use cortical thickness, surface area, and volume. And cortical thickness is estimated as the distance between the white and the pile surfaces depicted on the right. And surface area is the area of the white matter surface. And cortical volume or subcortical volume is calculated as a product of those two. So now everyone knows what I'm talking about. I'm going to explain something about how the development of these measures is around childhood and around adulthood, because it dynamically changes between childhood and adulthood. For example, cortical thickness shows in prior studies a linear decrease between childhood and adulthood. Surface area expands more slowly, and it starts to decrease in late childhood instead of childhood. And sorry, this is for volume, and for surface area, it shows a little bit of the same nonlinear pattern, and it expands more slowly than cortical thickness. However, these increases, peaks, and decreases in brain development, they might reflect very important milestones in development. Yet it is currently unknown whether these developmental patterns reflected in, for example, attenuated or accelerated decline, so a faster decline or slower decline of brain development, whether that is indicative of a sensitive window where experiences have heightened effects on brain development. So that is what we try to find out. And possibly musical capability can be an enriched environmental factor influencing these brain developmental patterns, and specifically during a sensitive window. And there are many individual differences in musical performance, and only a few become the real experts that we know of. So for example, the Dave Brubeck quartet have their very specific timing and very difficult, complicated music. And I would like you to give you an example of this kind of music. Well, they became experts through intensive training, but also in combination with some genetic predispositions. So we know from prior study that 50% of the variance of rhythmic ability can be influenced by genetic factors. And what prior studies also show is that a very big part on rhythmic ability is also related to the inclination to practice. And what does that mean? The inclination to practice is that the likelihood that one will engage in musical training is larger. So that has an interaction effect. So we cannot speak of solely genetic or environmental effects. They also interact with each other. And a very big key element of music is beat perception and beat prediction. And without this, music sounds really off. So that is something someone really has to learn very well before becoming an expert. Music ability is also very important in the learning of other motor skills, language abilities, social interactions, but also, for example, mathematics. So it has a great influences on many cognitive processes. And finally, age of onset of musical training in childhood can also be an important contributor to individual differences in brain development. Therefore, studying how musical performance relates to brain development is very interesting for neuroscientists like me, because it offers the opportunity to investigate genetic and environmental factors that are related to brain plasticity. Well, a fundamental part of component of musical capability is what we call sensorimotor synchronization. And this can be measured with finger tapping paradigms. And I hope you understand it better if I explain what how sensorimotor synchronization is defined, because it's the ability to synchronize your movement to auditory rhythms of an underlying beat. So with, for example, finger tapping paradigms, you can relate the sensorimotor to an underlying beat by using a metronome, for example, or using music. Well, mastering musical performance, as I explained, requires intense practice, as musical performance is a very complicated task. So it involves many multiple sensory modalities in the brain, such as, for example, motor planning, the preparation of motor executions, the execution systems, but also very important affective processing. So the emotional processes that are involved in music. So therefore, the musicianship or the ability to perform music requires an interplay between distinct neural systems, including regions in both the motor and also the affective network. And I will explain to you what these regions are and why they are important. So for example, I don't know if you can see my mouse, but these frontal areas and sensorimotor regions, those are necessary, for example, motor preparation, but also the execution of motor skills, but also the perception of the emotional contact, because it's very much related to the more limbic system depicted on the right. Then, for example, the basal ganglia, that is important for memory formation, but also memory retrieval and other emotional processes that are involved in music. For example, the hippocampus, the amygdala, but also the caudate, the putamen, those are all much involved in the affective system of the brain. Then we have the cerebellum, which is this area on the right in dark gray. That is very much important for movement coordination and for the fine motor learning that you need when you learn to play an instrument, for example. And then we have the temporal lobe, and the temporal lobe is important for auditory processing, beat prediction, and perception. So all these kind of brain regions work together for you to become an expert at the end in musical performance. So musical training, specifically during a window of enhanced developmental plasticity, can be an important contributor to individual differences in structural brain development. So that's why I want to let you know what the aims were in the present study. We first assessed whether individual differences in these structural brain developmental trajectories in up to 3 measures of MRI data are predictive of sensorimotor synchronization performance, so the music performance task. And we did that in a group of children aged from 7 to 14 years of age. And we used a longitudinal framework of 3 waves, which I just explained. And as a second question, we wanted to know whether the shared heritability estimates between brain plasticity and sensorimotor synchronization performance are driven by the same genetic and environmental factors. So we were interested what the overlap was in heritability estimates. So it's a bit different than a normal classical twin model. We were interested whether the brain plasticity is influenced by the same environmental and genetic factors as sensorimotor synchronization was. And this is what we call a bivariate genetic twin modeling, and I will explain that further on. Not much is known actually about the effect of enrichment of environment on brain plasticity, because most study focused on deprivation of environment on the brain plasticity. So for example, stress, COVID-19 pandemic, socio-economic status, you can name it. So prior work reported that the greater the exposure to repetitive stress, the more they are associated children with accelerated brain maturation. So that means growing up faster actually in the brain. And I also, there's a paper of Tully that mentioned this with all kinds of its review papers. So you can read all kinds of papers that reported this effect. And I also wrote a recent paper, which is now preprint, about the pandemic effect that also showed accelerated growth when they experience more stress. So what they explain is that children in low socio-economic status environments show accelerated growth in brain, mainly in cortical thickness, and children in the high socio-economic status show delayed maturation. So they probably have longer periods, longer opportunity to learn instead of growing up faster, which is necessary for stressful environments. So based on the previous findings, we hypothesized that an enriched environmental factor, such as musical training and musical capability, supports brain plasticity during a sensitive window. So we expect that higher sensorimotor synchronization performances were associated with slower, so attenuated brain maturation. And this will be reflected in more gradual slopes of cortical thickness change than children with lower sensorimotor synchronization skills. And we also pre-registered these hypotheses beforehand. And just to give you a short introduction how we can measure this using our longitudinal twin design is I am part of the Leiden SIT twin study, which includes two large longitudinal cohorts. One is the early childhood cohort, which included children from 3 till 10 years old. And the present study includes data of the middle childhood cohort. So I'm focusing only on the side below of this slide. And we used these three MRI assessments, and on the fifth MRI, or on the third MRI assessment, on the fifth wave, we also included a sensorimotor synchronization task. So now you know how the design looks like in our study. And just to zoom in the last part that I explained, so we used 3 MRI assessments, and on the third time point, we included the sensorimotor synchronization task, but also we included questionnaire data involving musical experiences across their lifetime. And in this sample, we see that 36% plays or have played an instrument. Yeah, it's a normal population, so this was actually quite a good rate, actually. 23% practiced between 1 and 5 years already, and 4% already practiced more than 5 years. Then 6% started before the age of 7, 26% after the age of 7, and 64% did not start playing yet on an instrument. The sensorimotor synchronization paradigm that we used, I will explain how we created this paradigm and what we measured. So children were instructed to tap on a percussion pad and with their dominant index finger, either the right or the left index finger. And the first part was out phase, where children were asked to tap along alternately with the tempo that was produced by metronome, so where the arrows are below the figure. And the second part was music cued in-phase tapping. And here the children were asked to tap along with 4 different songs. They could do in-phase or out-phase. That was both possible, whatever they wanted. And they were tapping along with 4 different songs. So 2 more easy ones and 2 more difficult ones. So we could manipulate the difficulty a little bit. And one example of a more challenging song I will show you. And if you want, you can try to tap along with the song so you know what the difficulty is. And yeah, this is the song. I think you all know her, it's Billie Eilish. All the children knew her, of course, because we wanted them to be really much involved in the music. So we asked what kind of songs before we conducted this research were very popular in the Netherlands around that time. And we operationalized sensorimotor synchronization by computing how stable children tapped related to the beat. So we were interested in the stability. Okay. Then to explain a little bit more how we measure the genetic and environmental effects using twin modeling. Well, to disentangle genetic and environmental effects, we use the assumption of a classic twin model. And in here, both monozygotic and dizygotic twins are needed. So monozygotic twins share 100% of their genes. They're very much identical. And dizygotic twins are a bit similar as siblings, and they share 50% of their genes. And what we do is we correlate them. So the twin pair, this child 1, we compare them with child 2. And we see how much they correlate in some behavior. And if they correlate very high within monozygotic twins and very low in dizygotic twins, we know that the genetic effect has a key role in that outcome variable. So for example, a brain region or brain development. However, if both monozygotic and dizygotic twins score very high correlations in both cases, we can also say there's an additional effect of shared environment. But also, for example, if monozygotic twins show very low correlation and dizygotic twins show high correlation, we also know that shared environment plays a role. So these are the assumptions that we also implement in a more difficult model, because I already told at the beginning of my presentation that we used bivariate ACE modeling to really understand whether same heritability estimates both influence brain plasticity and sensorimotor synchronization. We do that using the bivariate ACE model in which we can very specifically estimate in A, genetic factors, in C, shared environment, and in E, unique environment. And by calculating the covariance between the two variables that we're interested in, and then estimate how much of the contribution is driven by genetic, shared, and unique environments, we can calculate how much of, for example, environmental input is shared in the two variables that you want to include in your study. I will spare you the technical details, but if you have questions about it, I can answer it later on. So our behavioral results reveal that children perform best in stability tapping in the out phase tapping conditions. And that was compared to the more simple song conditions and the more challenging song conditions depicted on the right. And these 5 conditions we used as outcome variables of sensorimotor synchronization performance in our neural growth models, which I will explain later on. And we did this because we wanted to manipulate the difficulty in the task. So we were curious about whether children were indeed better in the out phase. The out phase conditions compared to the more difficult music conditions, because in a music condition, there's much more involved than just a metronome, because they hear many melodies and rhythms that are just combined into one song. And as an exploratory analysis, we revealed that children in the high socio-economic status group were much better, well, not much better, were better in stability tapping compared to children in the middle SES group. And the effect was mainly explained by the total amount of time that the children played on an instrument. So what these findings suggest is that probably the children in the high SES group had much more access to resources of playing an instrument or go to lessons, for example. Our group of low socioeconomic status is quite limited. So therefore, we could not find a difference between these groups, we think, because only 6.3% of our population were included in the low SES group. Yes. Then I will move on to our neural results. And what we've found is that 6 brain regions were indeed associated with sensorimotor synchronization performance. And first of all, I want to show you how the developmental patterns of these brain regions look like. So we found 2 regions in the cortical thickness dimension of MRI. And if you look at the main developmental pattern, it all decreases, which is in line with prior studies reporting this. We also found a surface area brain region. The post-central region was also involved in the preparation of motor skills. And for subcortical volume, so more the affective network, we found cerebellum and amygdala volume. And as you can see, the growth patterns are a bit different. So for cortical thickness, we see that the overall growth is decreasing between 7 and 14 years of age. Surface area is a bit more stable, but also decreases. Only it depends if you're a boy or a girl. And for subcortical volume, it increases still from 7 to 14 years of age for the amygdala and the cerebellum volume. And what I want to show you, why I want to show you these figures is that if you look closely, you see all these individual lines in the graphs, very interesting personal lines. And we were interested in whether these individual trajectories, whether these were predictive of sensorimotor synchronization performance. And well, indeed, 6 out of 15 regions show to be associated with music performance tasks that we used. And how did that look like? So these are a bit more complicated graphs, but I will show you what we did. Is here I present the 6 regions of interest that show to be associated with sensorimotor synchronization. And they were associated to the simple songs, but also to sensorimotor synchronization in the more complicated songs. So the music acute in phase tapping was this. And in line with our hypothesis, we observed that indeed attenuated brain development or a delay in brain development of cortical thickness in 3 brain regions and development of volume in 2 subcortical regions were associated with better sensorimotor synchronization performance. And how can you see that? Because on the x-axis, I represent the slopes of the region of interest. And on the y-axis, we represent the stability tapping. And for example, if we look at these 2 figures, we know that cortical thickness, because this is a cortical thickness measure, it normally decreases over time. And this graph shows that the less it decreases, so it's when slower maturation is displayed, the higher the sensorimotor synchronization is. This is a bit different for example, the cerebellum, because the cerebellum increases instead of decreases over time. And here we show that the less it decreases, the higher the sensorimotor synchronization performances are. And yeah, that's why you don't see the same direction of effect all the time, because we talk about different dimensions of MRI. And therefore, it shows different directions in the graph. However, there are also 2 areas that showed accelerated growth in brain development, in the fusiform gyrus and the postcentral gyrus. And we suggest that given the fine motor skills as well as the rhythmic discrimination that takes place in these two regions, that there are needed to synchronize with the beat of very complicated rhythmic sounds, and therefore very high plasticity and accelerated growth is needed, so faster thickness. So some of the areas need to show attenuated, but some need to show accelerated growth because they need to learn fast how rhythmic discrimination works, for example. And as a sensitivity check, since we found that in all the prior studies, we wanted to know whether these effects were driven by SES, for example, but in all the associations, SES did not influence the individual differences in brain development. So it was not explained by SES. Then for our second aim, we estimated the genetic, shared, and unique environmental factors. And what we revealed is that for the covariance of the regions of interest development and sensorimotor synchronization performance in the simple sounds, there was a mix of genetic, shared, and unique. However, mainly shared and unique environment of sensorimotor synchronization performance also was a factor that influenced brain plasticity. And on the right, we can see actually the same effect. So mainly unique environments, in some cases shared environments, and only two of the regions also genetic inputs that influenced both behavior and brain development. And this is a very nice way to really see how brain plasticity takes place and what kind of input or what kind of contribution of input is most important in this case. So I would like you to take away from this talk that we indeed find a relation between structural brain developmental regions, trajectories of the motor network and the affective network. So that was a start. Second, we were interested on how the direction of that effect was, and we found that mainly attenuated brain development was correlated with higher sensorimotor synchronization performances. And we suggest that there is a possible sensitive window indeed between middle childhood and early adolescence, where enrichment of an environmental factor such as musical training affects brain development trajectories to a larger extent. And it might mean that that attenuated brain maturation might be an effect of prolonged brain plasticity. So the opportunity to learn for these children become perhaps longer than when a children needs to develop faster in brain. Because all children at the end show a regression to the mean. So they all decrease, but some slower than the others. So the window of opportunity become larger, we think. And then at the end is that we also observed that a substantial part of the relation between brain development and sensorimotor synchronization was driven by shared environments and unique environmental factors. So possibly musical practice, we think, as an environmental factor, has a larger influence than musical talent on individual differences of brain development. And because I think you guys are a group of mixed neuroscientists and teachers, I also want to include a slide. What does this mean for society? So I'm quite a fundamental researcher, and I know what happens in the brain, which is a very cool fact that it has indeed an effect in brain on how good you are at music. But how can we implement this in society again, and how can we implement this in school classrooms? So what important is, I think, is that music can be good for brain development, but it can also improve many articles that I found in social interaction, for example. So the bonding between people, it improves the well-being, the quality of life. And because you learn these very complicated sensorimotor integration skills. Those are also skills that you can implement in many other cognitive processes. So music is very special in this way. Also playing sports, for example, to predict how you hit the ball at the right time. Those are all very good processes for other cognitive processes in your life that you need as well. Another thing that I would like to mention is that I think in the Netherlands, we can much more involve music in classes than we're now doing at the moment. People are even getting the musical part out of the educational programs because they think, no, we need to focus more on the mathematics and the cognitive part of the developing brain. However, our queen, Maxima, she's very much involved in the MindUs program, and this program stimulates also the initiative for healthy development. So how to be vulnerable, how to use a growth mindset. And she's also much involved in children with lower SES backgrounds and music programs. And she also thinks that by inducing music programs, people in more deprived environments can perhaps show an improved effect by learning to play music instruments, for example, because it also stimulates social interaction, but it's also good for brain development, as I just showed in my presentation. And the final one is, it's something that I watched a while ago, that before children go to high school, they are very explorative, and they look a little bit like researchers because they are testing all these kinds of things to understand how the world works around them. And you can really train that state of mind with music, because that also helps to create a playfulness, a creative and an open-minded state. And of course, we also need the abstract state of mind where children learn to include mathematics, reading and writing in their schools. It's very much important, but isn't it the time to combine these both? I think playing music is just as important. And if we see that effect of socio-economic status, that they are more trained in music and perhaps better in music, because they have many more resources. So we need to help the children that are in low socio-economic statuses, for example, to get free lessons or just to get educational programs, including music at school. So I want to thank you. I see it's 35 minutes. I want to thank you for listening. And I also want to thank the team, which is not included in his presentation, but I worked very much closely to all these people depicted on the left. And we wrote a pre-registration about the study. So if you're interested, you can read that here. And if you have questions, I'm very happy to answer these.
Thank you so much. That was a really interesting talk. I'll give you like kind of real life clap. So we have a question in the chat. Barbara says, there is so much going on in studying connectivity and how connections between areas of the brain change with, for example, training in meditation or training of various sorts. Are you planning to do trait as opposed to state-related connectivity studies in the future? I think this could be fascinating. And then there's some examples of papers given where that's been done.
Oh, really cool question. No, I'm not planning to do that in the near future, but I think it's really interesting to look into. For example, training meditation or training of various sorts. Are you planning to do traits? Connective studies in the future? No, for now, I'm mainly focusing on environmental effects that are becoming a trait actually, that involves brain development. But perhaps someone can, the one that asked this question can perhaps give me an example of connectivity studies that they're dived into and which has an interesting finding on brain development. Does anyone can give that example?
Barbara, did you want to say anything about that?
Was that the question for me? On that, I posed this question. I gave a couple of examples in the chat. So there's several papers there. There's so much going on, and it seems like you can see very quickly changes through training over several weeks or even over several sessions. For example, when doing meditation studies, you can see connectivity changes in the brain very quickly. Mm-hmm. Whereas I would think that you could see changes in the thickness of the cortex. It would be really, really slow and very difficult to find that kind of thing over time, where connectivity changes are really, relatively rapid, relatively immediate to detect. And, so it just may be a possibility for you to study that's much more, that's much quicker, in revealing what the effects are, because sometimes it's not like a change here and a change here. It's actually the changes in the connectivity that are what really matter.
I agree. Yes, I agree. Yeah, there is a bit of a slower maturation or brain plasticity going on when we talk about cortical thickness compared to connectivity, for example. However, not many studies have dived into this yet. So, for example, in a study that I wrote a preprint about, is that we already also found cortical thickness plasticity when children experienced the pandemic only in a few months already. So they showed accelerated growth. So perhaps it's going a bit faster than we think, because I also, prior to that study, I thought, okay, it will not change within such a short period of time, but it also changes quite quickly. But I agree with you that the connectivity changes a lot faster in a shorter period of time. It will be interesting to dive into that as well. Also when looking at music, for example. Yeah.
Oh, yeah. Boy, well, you're set up so that, and I think the studies you're doing are really fascinating. And so the engineer part of me says, okay, well, what are the connection changes that are driving those, that increase or decrease in thickness?
Yes,
that's what we would love to see. Yeah.
Yes, because we don't know yet. I also wrote that in this paper that is currently under revision in the neuroimage, that we don't know what exactly is going on. Is it because of cortical thickness decreases faster or surface area increases faster? Because they're all interconnected. Or is it, do we need to talk about the volume? That's why we included all these different MRI dimensions, because we're not completely sure what the underlying mechanisms are. Is it the myelinization, indeed, for example, so the connectivity in between the regions? So yeah, that is something that we still need to dive into. What are the exact underlying brain mechanisms that cause this plasticity?
Yes, and I think by looking at it in terms of causal analysis, which you can do, you can actually see more of what's driving those changes in plasticity rather than just observing the changes. So it's the connections that are as important, or even sometimes more important than the cortical thickness. So I don't know. I would encourage, because I think that combined with what you're doing, that just would be, wow, we would all love to know, even more about what those causal effects, are, and what's driving those changes.
Yeah, I completely agree. I write it down, and perhaps it's nice for a future study also to dive into more. Yeah. Thank you.
Thank you. Some really interesting points there. We have a question from Astrid in the chat. She says, you mentioned that in one of your studies, you had a very small number of low SES participants, and this is probably why a significant difference between them and the middle/high SES groups wasn't found. How were participants recruited for this study? And have you thought about adapting your recruitment methods in the future to try to access more lower SES participants?
Yeah, it's a very good question. So we included these participants 10 years ago already, when they were first included in the first MRI assessment, and they were included through municipal registries. So the whole western part of the Netherlands was invited to participate in our study, and yeah, many people applied. However, yeah, the people that were actually most difficult to find, I think they didn't apply at the moment. And I think we need to change these strategies looking at it now. And my lab is also working on that very much, because now we moved to Rotterdam, which is a very mixed city in the Netherlands, where we really want to involve all kinds of populations. And we see, like 10 years ago, the attention on really have a very good divided population was less on the agenda as it is right now. So yes, if we really want to capture those SES groups, we need to make more efforts to get in contact with these kind of families. So I don't know if that answers your question.
Great. I think it's a problem we often face in these kind of studies where,
we need to pay more attention to it, and we need to work harder for it if we really want to understand the whole population. And now we were still very happy that we also have a middle SES group, because sometimes you have samples that only include high SES children or adolescents. But still, the very low SES group, it was difficult to find and to include in our study. And I agree that we need to pay more attention to that. Yeah.
I also have a question about your participants. So you have these two waves of the study. So I was interested in why you looked at the older group compared to the younger group in terms of like musical experience.
Yes, so I will show you the design again, because I was interested in MRI brain development. So let me see this one. I was interested in the MRI brain development, and we only implemented that from 7 years old. And that has the reason because when you, it is already quite a young age. If you include children younger than 7 years of age, there's a lot of movement going on. So even when they were 7, we had to exclude quite a lot of participants because they moved a lot in the scanner. So prior to this design, they decided, okay, we do 2 cohorts. In the first cohort, we only implement MRI in the 7 to 9 year group. And before that, we do EEG measures. So children from 4 to 7, they were also measured using EEG. Using EEG. But the behavior components are a bit similar over these 2 cohorts. So we used, this is actually a study design that try to understand how social competence and behavior control develops. And the middle childhood cohort is more focused on brain development in that as well than the younger cohort. So that is why we chose only the middle childhood cohort.
Yeah. Okay, that makes sense.
But it's really cool because with this design, a colleague of mine also used a replication, for example, because these are the same age but different children, and she was interested whether we could replicate findings between those 2 MRI measures above, so on from 7 to 9 years old. So yeah, we can do a lot of cool things with this design, but sometimes we just need to choose one of them.
Right, that makes sense.
I'm mainly focused on the middle childhood cohort in my whole PhD project. Yeah, so I'm almost at the end, so I almost wrote all of my papers, and they're all involved in the middle childhood cohort. Yeah.
Okay, Brilliant. We have another question. Eliana asks, when you mentioned musical training, did it include playing an instrument, reading music, or both, or singing? What kind of stuff?
Yeah, very good question. So we asked whether they were included in playing an instrument, or if they already played an instrument but not anymore, because we wanted to know if they played an instrument once in their life. And we also asked whether they sang or not. So we took them both in our musical training questionnaire. Yeah. And I think there are differences because playing an instrument and singing are two different things. So in a future ID or a future study that dives more into this subject, can also check whether type of instrument or singing indeed has a different effect on brain development. And now we just put them on one measure. Yeah.
Great. And I wondered if the amount of years of experience playing music or singing has like any effect. Is that something you looked at?
Sorry,
sorry. I said, did the number of years that the participants had of experience playing music or singing have any effect on like the trajectories of brain development?
Yes, we didn't check that. So we only checked for sex, so whether they were female or male, and whether SES had an influence on structural brain development. But we didn't look at whether training has an effect on the intercept or the slope, and that has an effect on brain development. Maybe something cool to dive into as well. Yeah, but we didn't check that yet in this paper.
Okay. Irene asks, do you have any predictions, re the role of musical training in gross motor skills using your study design?
What do you exactly mean with the gross motor skills?
Gross motor is like not like writing and drawing, not like things that require like fine motor control, sort of bigger scale actions. Possibly someone can explain that a lot better than me.
I don't know which one asked the question.
Yeah, it was Irene. Maybe she was.
I'm having problems with my technology here. I hope you can see me and hear me. Yeah. Yes. So I was interested in the whole idea of looking at the role of musical training in sort of anything motor related. So in my field, sort of developmental psychology using epidemiological data, there is this distinction between fine and gross motor skills. So gross motor skills in sort of early childhood, walking, sitting, imitating actions, that sort of thing. The distinction is artificial to an extent, but it's very useful diagnostically in a lot of ways. So I was thinking in terms of how you see the role of music in anything to do with motor. Have you thought about how it can, extend to other areas of anything motor related?
Yeah, so I found actually many papers that music training is because you improve your sensorimotor integration in the brain so much that it also improves other motor skills. And there are studies that comparing, for example, music and sport-related motor skills, and they see that the children who learn to integrate the sensory and the motor skills and also the auditory systems and how they predict that on another beat, that it really helps them also in indeed walking in and actually predicting their environment around them. And that is that's a very important key aspect in motor skills, right? To predict how you walk or where you have to pay attention to, or how fast you can run. So yes, I think it is really much of a, we didn't test that in our study, but I saw many prior studies that investigating this as well. Yeah.
Okay.
I think music is really special in this way. So if we look at it the other way around, sport is also really special. because you have to include all these kinds of sensorimotor impulses. But music also includes the auditory system. So you need to predict how your movement is, but you also need to understand the rhythmic discrimination. You need to understand the melodies that are going on. So like every state of mind, every network in the brain is included. Yeah. So that's why I think it's so good to just implement it again in school classrooms, because it improves also other developmental.
And I was wondering actually whether it may be particularly beneficial for certain special child populations.
Sorry, but that it's mainly important
I was wondering whether, in fact, musical training may be even more beneficial for certain special groups, sort of kids with special educational needs or certain sort of disabilities. It may be an indirect but very effective way of managing improvement in the lives of these children, actually.
Yeah, I totally agree. I think because we have a very typical developmental sample, but I think it's so interesting to test this in atypical developmental samples, and I think it really helps. So also, for example, children who grow up in low socio-economic status worlds, so those are not disabilities, for example, what you mean, but we think that people also in more stressful environments can have a good effect of music again. So when they incorporated that in their lives, they can perhaps stimulate brain plasticity again instead of that it's going faster. So perhaps it helps in more harsh environments as well, especially for children that are living in more harsh environments or have disabilities or have more difficulties in education, for example. I think so, but we don't have the population to investigate it, but it will be so interesting, I think. Yeah. Definitely. And this, what we measured is, those are all amateurs. So these children, they just play some music once in a while. And even then we already see that effect. If we test this in a very professional group of musicians, the effects are probably much more present. So it's very interesting that we already see this in amateurs.
Great. I think we have possibly time for one more question from the audience, if we have any more questions. Just wait 1 second.
There's one question I see from Kim. Did you include?
Yeah, I think you kind of covered that by saying you have a typical sample. Yeah.
Well, we have differences in IQ. However, I did not include that in our brain developmental analyses, because I also noticed that some of the models didn't converge anymore if we put it too much covariates. But indeed, also IQ has an influence on individual differences in brain developments. We didn't think it has an effect also with sensorimotor synchronization in this way, but perhaps it's interesting to include it in future studies as well.
Great. Well, I don't think there's any more questions. So I'll thank you again for speaking to us today. It was really, really interesting work and just beautiful slides as well. Like, I need to know how you make your presentations.
Thanks.
You've got some thank yous in the chat and also some people reflecting on music in the classroom. So it might be nice for you to read the comments. Yeah, and I hope everyone will join us next week for our next session at the same time. Thanks again, Lina.
Yeah, thanks for inviting me. It was
Thank you.
Bye.
Bye. Thank you.